For most of the 20th century, communication between machines depended on physical connections. Telephones required copper wires. Computers, when they began to appear in offices and research institutions, were fixed to specific locations by cables. Early computer networks relied on wired infrastructure such as coaxial cables and, later, Ethernet. These systems were reliable and fast for their time, but they imposed a fundamental limitation. Mobility was impossible. A computer could only communicate if it was physically connected to the network. As computing spread beyond large institutions into universities, offices, and eventually homes, this limitation became more noticeable. Desks were arranged around network ports. Entire buildings were designed to accommodate cabling routes. Any change in layout required new wiring, adding cost and complexity. Laptops began to appear in the 1980s and early 1990s, promising portability, but their usefulness was restricted the moment a user needed network access. Portability in computing existed in theory, but not in practice. At the same time, the internet was growing. Email, file transfer, and early web services increased the value of being connected. The gap between what users wanted, seamless access anywhere, and what technology allowed, access only where cables existed, continued to widen. This mismatch defined the core problem that wireless networking would eventually solve. By the late 1980s and early 1990s, computers were no longer rare or specialized tools. Businesses relied on network systems for daily operations. Universities depended on shared digital resources. Homes were beginning to adopt personal computers, often with dial-up internet connections. The idea that connectivity was optional was fading. Access to networks was becoming essential. At the same time, work patterns were changing. Offices began experimenting with flexible workspaces. Portable computers were used in meetings, laboratories, and classrooms. Yet every mobile device still had to return to the wall to connect. This dependence on cables limited efficiency and undermined the promise of mobile computing. Attempts to solve this problem already existed. Early wireless communication systems were available, but they were either too slow, too unreliable, or too expensive for general use. Many were designed for specialized environments such as military communication or point-to-point radio links, not for dense indoor spaces like offices and homes. Radio signals behaved unpredictably indoors, bouncing off walls, furniture, and metal surfaces, creating interference that corrupted data. The problem was no longer whether wireless communication was possible, but whether it could be made fast, reliable, and affordable enough for everyday use. Solving this required more than incremental improvement. It demanded a fundamental advance in how wireless signals were processed. The key ideas that would later enable Wi-Fi did not originate in consumer electronics companies or networking firms. Instead, they emerged from advanced scientific research, particularly in radio signal processing. Scientists working in fields such as astronomy faced problems that closely resembled those encountered in indoor wireless communication, even though their goals were entirely different. Radio astronomers attempted to detect extremely weak signals from space. These signals were often distorted by noise, interference, and reflections, challenges similar to those faced by wireless data signals bouncing around a room. To extract meaningful information, researchers developed sophisticated mathematical techniques to separate signals from noise and reconstruct original data accurately. This research environment emphasized precision, collaboration, and long-term problem-solving. Solutions were judged by their robustness and theoretical soundness, not by immediate commercial value. It was within this context that critical techniques were refined, techniques that would later prove essential for reliable wireless networking. The importance of this stage lies in its distance from consumer products. Wi-Fi was not invented because someone wanted to remove cables from homes. It emerged because researchers were solving deep technical problems related to signal distortion and interference. Only later did the relevance of these solutions to everyday connectivity become clear. Once the core technical challenges were solved, wireless networking could finally move beyond experimentation. Reliable data transmission in complex environments became possible. When these solutions were standardized and combined with affordable hardware, wireless networking transitioned from research to infrastructure. Wi-Fi succeeded because it aligned perfectly with real-world needs. It removed physical constraints without sacrificing reliability. It allowed devices to connect automatically without specialized setup. Importantly, it scaled well. The same underlying principles worked in homes, offices, airports, and public spaces. Unlike many technologies that require users to adapt their behavior, Wi-Fi adapted to users. Connectivity became expected rather than exceptional. The technology faded into the background, becoming an invisible layer supporting communication, commerce, education, and entertainment. The ultimate success of Wi-Fi was not marked by a single dramatic moment, but by quiet adoption on a global scale. It reshaped how people work, learn, and interact, not by changing human behavior, but by removing barriers. This success set the stage for the individuals and research efforts behind the technology, whose contributions were foundational rather than visible. John O'Sullivan was born in Australia, a country with a strong but often understated tradition in scientific research. His early environment did not revolve around invention or commercial technology, but it did encourage structured thinking, curiosity, and education. Like many future scientists, O'Sullivan did not grow up intending to invent anything. His early years were shaped instead by exposure to mathematics, physics, and disciplined study, fields that reward patience rather than spectacle. Australia's education system placed strong emphasis on fundamental sciences, and this environment suited O'Sullivan well. From an early age, he demonstrated an aptitude for analytical thinking rather than mechanical tinkering. He was drawn to understanding how systems worked at a deeper level, particularly through mathematics. This orientation would later define his entire career. Instead of building devices directly, he focused on the theoretical and signal processing foundations that make complex technologies possible. Importantly, O'Sullivan's early life did not involve commercial pressure or entrepreneurial ambition. His formative years were academically oriented, with success measured through problem-solving ability and conceptual clarity. This grounding ensured that his later work would prioritize correctness, robustness, and scientific rigor over quick results. John O'Sullivan pursued higher education in physics and mathematics, ultimately earning a PhD. His academic path was demanding and deeply theoretical. Rather than specializing in applied engineering, he focused on signal processing, electromagnetics, and complex mathematical models, areas that are often invisible to the public but essential to modern technology. During his doctoral studies and early academic career, O'Sullivan worked on problems involving signal distortion, noise reduction, and data reconstruction. These problems required advanced mathematical tools and a strong understanding of how signals behave in unpredictable environments. This work was intellectually rigorous and slow-moving. Progress was measured in equations refined, models tested, and assumptions challenged. Crucially, O'Sullivan's training emphasized collaboration. Scientific research at this level is rarely solitary. Ideas are tested through peer review, group discussion, and incremental improvement. This collaborative mindset would later be reflected in how Wi-Fi emerged, not as the work of a single inventor, but as the outcome of a research team contributing complementary expertise. His academic discipline also reinforced a long-term perspective. Solutions were not judged by immediate usability, but by whether they held up under varied conditions. This focus on generality and reliability would later prove essential when the same techniques were applied to wireless networking in crowded indoor spaces. One of the most important phases of O'Sullivan's career occurred not in computing or telecommunications, but in radio astronomy. He worked at Australia's National Science Agency, CSIRO, Commonwealth Scientific and Industrial Research Organisation, where researchers studied faint radio signals from space. Radio astronomy, posed extreme technical challenges. Signals arriving from distant galaxies were extraordinarily weak and easily overwhelmed by noise and interference. Extracting useful information required advanced signal processing techniques capable of separating meaningful data from distortion. O'Sullivan and his colleagues developed and refined mathematical methods to address these challenges. The research culture at CSIRO was methodical and non-commercial. Projects often spanned years. Success depended on precision rather than speed. This environment allowed O'Sullivan to focus on foundational problems without concern for immediate application. Importantly, it also encouraged solutions that were robust across many scenarios, an essential characteristic for later use in wireless networking. Although the work was aimed at astronomy, the underlying problems were structurally similar to those faced by wireless communication systems. Signals bounced, interfered, and arrived along multiple paths. The techniques developed to handle these effects would later become central to Wi-Fi technology, even though this application was not initially anticipated. John O'Sullivan's personal life remained largely private and stable throughout his career. Unlike many high-profile inventors, he did not cultivate a public persona or media presence. His focus remained firmly on research and problem-solving. This personal restraint allowed him to work within long-term institutional frameworks rather than pursuing individual recognition. Stability in personal life often plays a quiet but critical role in sustained scientific achievement. O'Sullivan's career required deep concentration, patience, and continuity, qualities supported by a balanced personal environment. He did not shift frequently between roles or industries, choosing instead to remain within research institutions where complex problems could be explored thoroughly. This orientation also shaped how credit and recognition were handled. O'Sullivan's work on the core technology behind Wi-Fi emerged from collaborative research rather than individual entrepreneurship. As a result, his contributions were embedded within patents and standards rather than branded products. This understated role aligns with his broader professional character, influence without visibility. By the time the relevance of his research to wireless networking became clear, O'Sullivan was already an established scientist with decades of experience. His early life, education, and professional environment had prepared him not to chase applications, but to produce solutions capable of scaling globally once the opportunity arose. John O'Sullivan's path toward Wi-Fi did not begin with consumer networking or the Internet. It began with a narrowly defined scientific problem inside radio astronomy: how to accurately reconstruct signals that had been distorted by interference, noise, and multiple signal paths. In indoor wireless environments, radio waves reflect off walls, ceilings, and objects, arriving at a receiver at slightly different times and angles. In astronomy, radio waves arriving from space faced similarly complex distortions. At CSIRO, O'Sullivan and his research colleagues were working on mathematical techniques to correct these distortions. The goal was to improve the clarity and accuracy of astronomical observations, not to build communication systems. The work focused on signal processing algorithms capable of separating overlapping signals and reconstructing original data despite interference. This stage of the journey is important because it shows that Wi-Fi did not emerge from market demand or product design. It emerged from pure problem-solving. O'Sullivan's task was to make unreliable signals reliable, not in homes or offices, but in scientific instruments pointed at the universe. The solutions he helped develop were abstract, mathematical, and general purpose, with no immediate application to consumer technology. One of the most critical challenges in both radio astronomy and wireless networking is multipath interference. This occurs when a single signal reaches a receiver through multiple paths, each delayed and altered slightly. Instead of receiving a clean signal, the system receives overlapping versions of the same information, which can cancel each other out or create errors. O'Sullivan worked on algorithms that could model and correct these effects. Rather than treating interference as random noise, the approach treated it as structured information that could be mathematically analyzed. By understanding how signals combined and interfered, it became possible to reconstruct the original transmission with high accuracy. This work required deep understanding of Fourier transforms, probability theory, and signal modeling. It also required computational efficiency, since real-world systems must process data quickly. The resulting techniques were powerful but subtle, hidden inside equations and software rather than visible hardware. Years later, when engineers attempted to build reliable high-speed wireless networks inside buildings, they encountered the same problem. Radio signals bounced unpredictably, limiting speed and reliability. The techniques O'Sullivan had helped develop were suddenly relevant outside astronomy. They offered a way to turn multipath interference from a problem into an advantage, enabling higher data rates rather than reducing them. The connection between O'Sullivan's research and wireless networking became clear during the early 1990s as demand for wireless data increased. Engineers struggled to create systems that could operate reliably in cluttered, indoor environments. Traditional radio techniques failed under these conditions. At this point, O'Sullivan and his colleagues recognized that their signal processing solutions could be applied to wireless communication. The algorithms originally designed to extract faint cosmic signals could be adapted to reconstruct digital data transmitted over radio waves in buildings. This realization marked a transition, not from science to business, but from one domain of application to another. O'Sullivan did not abandon research principles. Instead, he applied them to a new context. The work remained technical, mathematical, and collaborative. It was formalized through patents rather than products. Importantly, this transition did not involve designing consumer devices or networking protocols. O'Sullivan's contribution lay in the core method that made reliable wireless communication possible at high speeds. This method became part of the foundation on which later standards, including Wi-Fi, were built. The final stage of O'Sullivan's journey to Wi-Fi involved standardization rather than invention in the traditional sense. For a technology to succeed globally, it must be standardized so that devices from different manufacturers can work together. Wi-Fi emerged through international standards bodies that combined contributions from many researchers and engineers. O'Sullivan's patented signal processing techniques became part of this broader framework. They were licensed and incorporated into the technology's underlying Wi-Fi standards. At this point, the work was no longer tied to a single institution or country. It became part of global infrastructure. What makes this journey distinctive is its indirect nature. O'Sullivan did not set out to invent Wi-Fi, nor did he design routers or consumer devices. His role was foundational. By solving a deep technical problem years before wireless networking became widespread, he enabled others to build practical systems on top of that solution. The success of Wi-Fi reflects this layered process. Breakthroughs often occur far from their eventual application. O'Sullivan's journey demonstrates how fundamental research, when done rigorously and collaboratively, can shape everyday life on a global scale, often without public visibility or dramatic milestones. Wi-Fi works by converting digital data into radio signals that can travel through air and be decoded accurately at the receiving device. At its most basic level, the process begins with binary data, ones and zeros, generated by a computer, phone, or other connected device. This data cannot be transmitted directly through space. It must first be mapped onto a physical signal. In Wi-Fi systems, this physical signal is a radio wave, typically operating in the 2.4 GHz or 5 GHz frequency bands. These frequencies were chosen because they can carry large amounts of data and are suitable for short-range, indoor communication. The digital data is encoded by modulating properties of the radio wave, such as amplitude, phase, or frequency. This modulation is not arbitrary. It follows precise mathematical rules that allow the receiver to reconstruct the original data even when the signal is weakened or distorted. The challenge lies in maintaining accuracy as the signal reflects off walls, floors, furniture, and other objects, an environment far more chaotic than open-air transmission. Wi-Fi succeeds because its signal design anticipates and compensates for this complexity. Indoor wireless environments create a phenomenon known as multipath propagation. When a Wi-Fi signal is transmitted, it does not travel in a straight line only. Instead, it reflects off surfaces and arrives at the receiver along multiple paths, each with a slightly different delay. This causes overlapping signals that can interfere with one another. Early wireless systems struggled with this effect, leading to slow speeds and unreliable connections. The breakthrough underlying Wi-Fi was the ability to treat these overlapping paths not as noise, but as usable information. Advanced signal processing algorithms analyze the timing and structure of the incoming signals, separating and recombining them to reconstruct the original data. This approach relies on mathematical techniques that model how signals behave in complex environments. By understanding the channel, the space between transmitter and receiver, Wi-Fi systems can adapt dynamically, adjusting transmission parameters in real time. This capability allows Wi-Fi to operate reliably in crowded rooms, offices, and public spaces where interference is unavoidable. The significance of this step cannot be overstated. Without effective multipath handling, wireless networking would remain limited to low speeds and specialized uses. This is where the foundational research contributed by scientists such as John O'Sullivan became essential. Wi-Fi must balance speed with reliability. Faster transmission rates increase the risk of errors, especially in noisy environments. To address this, Wi-Fi systems incorporate error detection and error correction mechanisms directly into the communication process. Data is transmitted in structured packets, each containing additional information that allows the receiver to check for errors. If errors are detected, the system can request retransmission or correct the errors automatically using redundancy built into the signal. This ensures that data arrives intact even when conditions are less than ideal. Wi-Fi standards also adjust transmission rates dynamically. When signal quality is high, the system increases data speed. When interference or distance reduces quality, it lowers the rate to preserve accuracy. This adaptability is one of Wi-Fi's defining strengths. Users experience this as a stable connection rather than a fragile one. Behind this apparent simplicity lies sophisticated coordination between hardware and software. Antennas, signal processors, and algorithms work together continuously, making decisions thousands of times per second. The user remains unaware of these adjustments, which is precisely the point. Wi-Fi hides complexity to deliver consistency. Technically, Wi-Fi is not a single invention, but a layered system. It combines radio transmission, signal processing, error correction, and standardized protocols into a unified whole. Each layer builds on the previous one, and failure at any level would undermine the system. What makes Wi-Fi enduring is that its core principles are scalable. The same methods that allow a laptop to connect in a home also support dense networks in offices, airports, and public venues. As hardware improves, these principles continue to support higher speeds without requiring fundamental redesign. The techniques originally developed for scientific signal reconstruction now operate billions of times per day across the world. Wi-Fi demonstrates how abstract mathematical solutions can become invisible infrastructure when they are implemented correctly. In essence, Wi-Fi works because it treats the environment realistically. Instead of assuming ideal conditions, it embraces interference, reflection, and noise as variables to be managed. This approach, rooted in scientific rigor rather than convenience, has allowed Wi-Fi to become one of the most successful communication technologies in history, quietly enabling modern life without demanding attention or explanation.